Hi, folks. Welcome to our latest installment for the Future Leaders in Robotics and AI seminar series. Thank you again for joining. If you want to watch any of the recordings of past or current sessions, then please go to our website, robotics.umd.edu/future leaders, to take a look at some amazing talks. So today I have the honor of introducing two really great seminars. We have Sheng Cheng from University of Illinois Urbana-Champaign, and then our second speaker will be Laura Zhang, who is a PhD candidate from the University of Maryland. So let me first introduce our first speaker and take a look at his bio. So Shang received his Bachelor of Engineering degree in Control Science and Engineering from the Harbin Institute of Technology in China, and his PhD degree in Electrical Engineering from the University of Maryland College Park. He's now a postdoctoral research associate at the University of Illinois Urbana-Champaign. His research interests include aerial robotics, safe learning for control, aerial manipulation, advanced air mobility, adaptive control, and optimization. So with that, I will let you go ahead and talk.
Okay, thank you for the warm introduction. Actually, I'm going to share screen and let's see. Okay, can you see my screen now?
Yes.
Okay, awesome. And just to confirm, you can hear me clearly, right?
Yes.
Okay. All right, good to go. So, thanks for the introduction and good afternoon, everyone. My name is Shane, and I'm very happy to be here today talking about our recent work on DiffTune. So to get everybody on the same page, first of all, control is for stabilizing a system and hence to have the system tracking a certain reference signal. So to design controllers, the most prevalent approach is model-based, where one can follow the Lyapunov analysis to provide guarantees like stability or bounded tracking errors. And then model-based controller design also have the benefits of interpretable structure of the controller and also physical meaning of the parameters. Think about the PID or the LQR or the MPC. The parameters, you know what they're doing and you have an idea of what's going to change if you change the parameters. But the problem is controller tuning is really not an easy job. So why is that? Well, to answer the question, let's first take a look at the problem setting for controller tuning. First of all, you would have some system, a target system, and you can have a dynamical description using using the dynamics. And then you would have a target controller that can fulfill the control functionality of your system. And here we use a tracking control as an example. So the goal here is to track this XK bar as the reference using the feedback state XK, and the controller is parameterized by the parameter theta. And then the goal for controller tuning is to change parameter theta so that you can meet the performance metric of your system. And this performance metric is denoted by the loss function L. You can think about tracking error as an example of what you want to reduce of your system. So what happens when you do this by hand by this for this controller tuning? Well, first step, you're gonna collect the state and control actions, and then you can evaluate the loss function. You got this number, and then you say, okay, I'm going to change one parameter value and send it back to the system for another round of evaluation. So the key limitation here when you do this by hand is that you can only change one parameter at a time. And this is the major practice because if someone changes more than one parameter each time, say two, then it's hard to tell which parameter change leads to the performance change. And it's going to make the decision of the following parameter change harder. But changing one parameter each time really cannot scale with the dimensionality of your parameter space. And it's generally hard if the parameter space is bigger than 10. So to solve this problem, people have coming up with solutions called auto-tuning. So there are two main categories of auto-tuning so far. One is following the model-based approach, where the benefits are that you can leverage the prior knowledge of your system and also you can ensure the stability by design. But the caveat is, however, that the model-based approach mainly are based on simulation, which means that your systems, your real hardware, when you collect the data, and you cannot directly put it back to your simulation to get a new parameter. And rather, always have to follow this simulation to reality type of practice, and there can be same to real gaps. And then in the recent years, there's the rising of machine learning-based approaches which constitute the model-free auto-tuning. So normally they use the data-driven methods using machine learning models or tools like Gaussian process regression. And in general, in the model-free approach, there's almost no assumption on the system or the controller. But the problem when you put aside your system's prior knowledge, things are that the approach can scale poorly with the dimensionality of your parameter space. And also because of the loss of the prior information, it's hard to know when the parameters you obtain from the machine learning models can give you stability. So we asked the question, can we apply machine learning tools to model-based auto-tuning for, say, better efficiency? And the answer is yes. So we come up with this auto-differentiation enabled auto-tuning method called DiffTune. So the first step is to formulate tuning problem as an optimization problem. The goal here is to look for a parameter theta so that you can minimize the loss function subject to your chosen system dynamics and your chosen controller. And all we require here is that the dynamics and the controller are differentiable. And if you look at the literature, many controllers are shown to be differentiable in the recent years, like PID or optimization-based control laws like MPC, optimal control, or even CBF. And again, our solution is called DiffTune, which is a gradient-based method. It has the nice features of stability, efficiency, and also compatibility with real data. So how does it work? We start with the system, we collect the data, and then we can evaluate the loss function based on this single trial. And then we proceed to compute the gradient of the loss function with respect to parameter theta. And then with this information, we can apply gradient descent. So here we have a projected gradient descent to make sure that the new parameters we obtain each time is within the feasible set denoted by capital theta here. So this is the feasible set that can ensure stability of your system that can either come from theoretical analysis, such as Lyapunov analysis, or it can be empirically determined following expert experience. So with the updated parameter, you put it back to the system, reevaluate the system, and then repeat the procedure. And on the right, I show one example of tuning the controller for quadrature tracking control. So you can see here this blue curves, which represent the close-up tracking of the quadrature, is actually approaching the red reference trajectory through iterations. And towards the right, you can see the monotonic reduction of the reduced tracking error through iteration, which indicate increased performance. So the key here is to obtain the gradient of the loss function with respect to parameter theta. And how do we do that? Well, we first observed that you can decompose the target gradient using chain rule, and this breaks down to the sensitivity of the state and control action to parameter theta, which we call now sensitivity states. And then we can leverage the iterative structure of a dynamical system, take the partial derivatives to theta on both sides of the dynamics, and then you get this equations. So here, this is another state space system where the states are the sensitivity states. And all you have to do is to plug in the coefficients here that can come from the data you collected from real system to iteratively propagate it forward, which we call this procedure sensitivity propagation. And you can do this computation or this propagation in parallel to your system's evolution forward in time. So at the end of the horizon, you can compute the target gradient, perform the gradient update, and then get a new parameter and then restart it to iteratively update the system. So we compare our method with the state-of-the-art auto-tuning methods on a benchmark nonlinear quadrature control tuning problem. And the baseline approaches include Auto-Tune, which is a sampling-based approach using Metropolis Hastings sampling. And there's also a Bayesian optimization-based baseline called SafeOPT-PSO, which applies particle swarm optimization to address the scalability issue of Bayesian optimization. So we compare the three approaches on different trajectories, and the results are shown to the right. What you see here is the evolution of the tracking error through the iterations of the trials by these different tuning algorithms. So two things we conclude from these plots. One, DiffTune achieves the fast error reduction in the minimum number of trials at the beginning. So this is the efficiency of DiffTune. And the second point is that DiffTune can converge to the minimum error towards the end, showing the optimality of the resulting parameters. So these two features come from the effective usage of the first order information in the auto-tuning algorithm by DiffTune. And then we proceed to test DiffTune in experiments where we tune the controller for a quadrature to track an ideal circular trajectory. So DiffTune is able to reduce the tracking error by 3.5 times in only 10 trials as seen on the left here. And comparing with the best achievable human or manual tuning, we reduce the error by half, which is quite remarkable. And on the right, you can see the evolution of the 12 parameters being adjusted during this 10 trials. So one thing we can perceive here is really the nonlinear relationship between the parameters and the tracking error. And you can see here that the parameters actually change the direction in the middle of the procedure as a reflection of the landscape change of the loss function. So this nonlinear phenomenon, if you imagine the nonlinear landscape, actually requires many trials if you are to tune the parameters by hand. So this nonlinearity really uh, hinders the efficiency of tuning if one is to perform this by hand. So this video shows the 10 trials that we performed over the quadrature. What you can see is from the beginning, the quadrature can barely track this circular trajectory. And through iterations, the tracking conditions getting better, and towards the end, it can smoothly track this trajectory. And moving on, we also extend the usage of DiffTune to model predictive control, which is a popular controller choice due to its inherent handling of dynamics and modeling and the constraints. But tuning for MPC is also hard, and the reason comes from that the nonlinearity now comes in an embedded way from the iterative optimization algorithms. And then the high dimensionality of the parameters come from the fact that when we tune for the cost matrices, you can think about the quadratic cost like LQR. The Q and R matrices are the parameters you tune, and their dimension actually is squared of the dimension of the state and the control action, which can be quite tricky. So people have also studied the problem of auto-tuning of MPC, and in general, it's called parameter learning. And then there are also two categories. The first one is the open loop learning, where the goal is to improve the open loop optimal solution based on certain performance metric. And this can be done efficiently using using differentiable programming. But the problem is that open loop setting has a significant drawback for a short horizon. So this limits the application of open loop learning for MPC to mainly imitation learning. And then on the other hand, there's also the closed loop learning problem, which is actually the auto-tuning for MPCs. And the goal here is to improve the performance of a closed loop system that uses MPC as a controller. So existing approaches mainly explored probabilistic approaches that iteratively update a probabilistic model to guide the distribution of sampling. And the issue is that because it ignores the model information or the MPC structure, it can be rather inefficient. So we apply DiffTune architecture to MPC and utilize the efficiency of the differentiable programming and make the tuning problem serve for the purpose of closed loop learning. And the key here is to differentiate the MPC problem, which is an implicit differentiation. So here I use the simple example of a linear MPC as for illustration. So you have a quadratic loss function, sorry, cost function, linear dynamics, linear inequality constraints. And in order to obtain the gradients of this problem, all you have to do is to solve this auxiliary problem on the right, which share most of the parameters as the one on the left. And notice that the auxiliary problem also reduces the original linear inequality constraint into a linear equality constraint. So this is computationally much cheaper than the original problem, which makes the implicit differentiation computationally cheaper than the finite difference for the gradient approximation. So this table shows this procedure of how you can obtain the target gradient that's used for the sensitivity propagation by plugging in these values into these parameters to the auxiliary problem, solve it, and then the returning solution will be these gradients of interest. So we compare our approach with the baseline closed-loop parameter learning with MPC called the PSMPC that applies policy search to find the optimal parameter, and it uses a probabilistic model to capture the distribution of the optimal parameters. We conducted comparisons over several systems on different trajectories, and we observed the efficiency and optimality of DiffTune one more time, thanks to the effective usage of the first-order information. And we also extend DiffTune MPC to bipedal robots. So in this case, there is a dilemma on the model choice. So you can pick a simplified model that's differentiable, but it has rather low fidelity, and it can cause the model mismatch and suboptimal parameters. And then you can also pick a high fidelity model that mitigate the same to real issue, but the model itself is not differentiable. So unfortunately, we cannot apply DiffTune. And on the right, you can see what happens if you don't have a well-tuned parameter, you cannot even finish a walking task. So we solve this problem by augmenting the simplified model with a data-driven module that improves the fidelity of the system and also preserve the differentiability. And we applied DiffTune and then got the resulting parameters that can track this walking trajectory well for this bipedal task. Okay, and another example we use the DiffTune is to the VTOL vehicles. So these vehicles are typically overly actuated and they need control allocation. So this actually results in the performance of these vehicles depending not only on the controller, but also on the control allocation. So here we apply DiffTune to this problem to jointly tune the controller of an LQR controller and an optimization-based control allocation. So the total dimension is 35 of the parameter space, and we achieve a better performance than the baseline approach. And down on the bottom right, you can see the tracking of the lift plus cruise vehicle for this transition flight that constitutes a rotor-borne flight in the beginning for takeoff, and then a cruise flight based on wing-borne flight for the horizontal maneuvers. So one last thing I would like to mention is that our open source toolset. So we open sourced two repositories, one for the explicit controller and one for MPC. So we have coded the sensitivity propagation and also the auto generation of partial derivatives and provide templates and examples for illustration. So you can just bring in your dynamics and the controller, use the tool, and then come home with your best parameter possible for your task. All right, so that's pretty much it. So for our ongoing and future work, we are expanding to online parameter prediction for on-scene tasks. So we noticed that nowadays people are dealing more and more with robots that have the learning capability to handle unforeseen tasks. But down to the low-level control, we normally use the factory design control parameters, which have limited generalizing capability. So our goal here is to enable an online prediction of optimal parameters subject to on-scene tasks that can come from the upper level learning modules for unforeseen tasks. And we hope that this can offer from the low level the true capability of generalization of the motion of our robots. And then we're also modifying our current paradigm to include a model learning step so that we can better handle the model mismatch between our model and our real system. And we also look into the non-differentiable systems as well as the trade-off between performance and robustness. So that's the end of my talk today. Thank you for your attention, and I can take questions now.
So we have one question here. What requirements are you making on the sensitivity of the system with respect to the parameters so you don't get stuck at local minima while updating via gradient descent?
That's a very good question. So actually within our current scheme, we cannot escape from that. So, um, worst case possible, when you find a local minimum, it's not a bad thing. It's better than what you started. But getting to the global minimum is challenging because of the possible nonlinear landscape that come from the nonlinearity of your controller and your dynamical system.
Great, thank you. Are there any other questions from the audience? Okay, well, thank you very much.